Welcome to a refresher lesson for trigonometric functions, properties, and operations. This is part 2 of a two-part series in the properties and operations section. And in this part, we are going to be focusing on how to use trigonometric identities. This video corresponds to the examples on a worksheet packet that can be found at my Teachers Pay Teacher store. In this video, I will explain the skills and steps necessary to complete all the examples on the worksheet. Please feel free to skip around to engage in the concepts with which you would like some help. So there are several trigonometric identities, and I've broken them up into 3 parts. The first part are the basic trigonometric identities. You should pretty much know these by heart. If you're not familiar with them yet, or if you've kind of forgotten them from having seen them in the past, feel free to pause this video for just a moment and take a look at them. But these are ones that get used a lot. They're ones that you should be able to come up with pretty much off the top of your head. And so these are the ones that I'm naming the basic trigonometric identities. Then we have the trig identities that are a bit more complex. They still do get used a bit more, especially in math classes and upper math classes as you continue on your math journey. So there's 3 of them here, the sum and difference formulas, the double angle formulas, and the half angle formula. Again, if these don't look familiar to you, go ahead and take a moment to pause the video. These are not ones that I would necessarily say you need to memorize, but you should be familiar with them. You should kind of know that they exist, know that they're out there, know where to find them if you need them. And then there's these other 3 trig identities, which in my experience are a bit more obscure. We don't use these very often. They are there. They can be used in certain situations, but these are not necessarily ones that you need to pay a lot of attention to, in my opinion, unless, of course, you have a teacher who is asking you to use these in their class. So the purpose of the identities is to give you something that will replace something else. No matter what you put in for the variable, it always is equivalent. And so you can literally replace one trig expression for another one using these identities. And the reason we want to have these identities is to do some simplifying, to take more complex kinds of trig expressions and try to make them something simpler, kind of break them down a little bit. To do this, you kind of have to go back and forth between using identities and using algebra. So when you're using identities, obviously, the point is to take something that's in the expression and replace it with something else. But when you do that, I always want you to ask yourself 2 questions. Is it a legal replacement, meaning that what you're putting in really is equivalent? And is it a helpful replacement? And that means, like, is replacing the original with this new thing actually going to move you forward in trying to break down the expression and make it simpler? Does it give you a next step to follow? So always keep that in mind. And I'm going to try to use that kind of language as we go through an example or 2. Also, when you're using identities, so many of the identities are based on sine and cosine that if all else fails and you can't really figure out how to move forward, change everything that's not already sine or cosine into terms of sine and cosine and see if that helps. Now, when we're talking about using algebra, we're talking about things like combining like terms. You can look for opportunities to factor things. If you're looking at a fraction, you might have common factors that can be canceled. If you have fractions involved that you're adding or subtracting, maybe we can combine those by finding a least common denominator. Or if you have one fraction that's a bit complex, maybe you can split it apart into two simpler fractions. And there are times where multiplying by a conjugate might also be helpful. So these are the kinds of tools and things that we have in our possession that we want to keep in mind. And it's kind of a back and forth. There isn't a prescribed do this first, then do this. You just have to kind of keep it all in mind and look for opportunities to use them. So when you are simplifying something, for example, we have here that we're being asked to simplify tangent squared of theta minus tangent squared theta sine squared theta. If you go back and look at the identities, there might be some different possibilities of things that you could replace. If you're looking at algebra, you might notice that there is a tangent squared theta in both of our terms being subtracted. And so what that tells us is that there may be more than one way to go about this, and some ways may be more efficient than other ways. So you want to try to keep that in mind. It's okay if you don't do it the most efficient way, as long as your process is mathematically sound. Okay, so I'm going to show you one way to do this, but then we can talk about some other possibilities. So for me, noticing that we have the tangent squared theta as a common factor in both terms means that I can factor that tangent squared theta out. And that's going to leave me with 1 minus sine squared theta in the parentheses. Now, one of the probably most used identities is our Pythagorean identity, where the sine squared of theta plus the cosine squared of theta equals 1. We can also use different versions of that. So for example, I can subtract the sine squared of theta from both sides and end up with a statement that says that the cosine squared of theta equals 1 minus sine squared theta. That is also a legitimate identity because it's just a version of the original. And so what that means is I can replace now the 1 minus sine squared with cosine squared. Now, is that legal? Yes, we just said that this is just another version of the Pythagorean, so it really is equivalent. And is that helpful? I would say yes, because it's taking an expression that is two terms being subtracted and replacing it with a single expression. So I think this will be helpful to me. So I'm going to try it. Now, one of the things I highly encourage you to do is to try something, see where it takes you, and if it's not taking you in the right direction after a couple of steps, go back and try something else. Don't be afraid to retry things and go back and go a different direction with something. Because sometimes you're going to think something looks good, and then you're going to get a couple more steps down the road and it's going to be a mess. Okay, so I'm going to try this for a couple of steps and see where it takes me. Now I'm looking at tangent squared of theta times cosine squared of theta. Well, now I can consider the identity that the tangent squared of theta can be rewritten as sine squared theta over cosine squared theta. So we're using the quotient identity, but because tangent is being squared, sine and cosine will have to be squared. And that is still being multiplied by the cosine squared of theta, which if it helps, you can make that a fraction also by putting it over 1. And by doing that now, you can see that the cosine squares of theta can cross cancel. And so I end up now with the sine squared of theta over 1, which ends up just being sine squared theta, which is a much simpler version than what we started with. So yes, we have actually simplified, sorry, we go. We have actually simplified. Everything works. It all looks good. Okay, I don't know why my iPad is being weird about this, but let's see if I can get this erased so I have a little space here. Very odd that my eraser is doing some weird things here. So sorry about this, guys. Give me just a second because I just need a little bit of space here to be able to show you another version. Okay. Maybe we can get this. Yes. Okay, good. All right. So that's one possibility. Now, somebody else might look at this and say, hey, you know what? I know that another Pythagorean identity is that 1 plus tangent squared theta is equal to secant squared theta. So if I use the same thinking as we just did with the sine squared plus cosine squared equals 1, couldn't I say that the tangent squared of theta is equal to secant squared theta minus 1? And yes, you absolutely can. So then you might be thinking, well, couldn't I then just substitute that secant squared theta minus 1 in for the tangent squared? So it might look like that. So again, here's where you need to ask those questions. Is that a legal move? Yes. Tangent squared theta really is equivalent to secant squared theta minus 1. So yes. Is it a helpful move? I would say no. To me, it looks like I just made my expression messier. Okay, so I probably would not recommend that you would take that step. Now, could it be worked out? Maybe. And you would have to see if you're really devoted to this substitution and you want to go with it, you can work it out. And if you can get to the sine squared theta as an answer, that's fine. But I think you're going to make it more complicated this way. However, there is another possibility that you could consider. Maybe you also want to think about the fact that tangent squared theta is equal to sine squared theta over cosine squared theta, which we used here, but you want to actually replace that first. Okay. Again, is that legal? Yes. Is it helpful? Maybe, because now you just have everything in terms of sines and cosines. So for some people, that might make this easier. Now, if I do a little bit of simplifying here, I'm going to take this sine squared times this sine squared, because technically that's just over 1, and make this sine to the fourth of theta over cosine squared theta. Now, because I already have a common denominator, I can go ahead and combine my numerators. And then in that denominator, I would probably look at the fact that I have a sine squared theta in both terms. And then realize again that 1 minus sine squared theta is the same as cosine squared theta. And since that's over a cosine squared theta, it means my cosine squared thetas can cancel out. And I'm left with the sine squared theta like I got in my first version. Now that took a few more steps to get there, but for some people that might be easier because everything's in terms of sines and cosines. Okay, so all this is to say that there are multiple ways in many cases of how you can get to a correct answer. You have to choose the steps that you're going to take to try to keep things as efficient as possible, easy enough for you and your brain. You need to make sure that you are using identities in a way that is legal and helpful. And don't forget about the algebra steps that you can take to make things easier. But don't be afraid to try something. And if it's not going where you want it to, go back and try something else. This is not an exact science. It's going to be a lot of trial and error. Now, another thing that you can use identities for is to find exact values for something when they're not one of the special angles on the unit circle. So for example, if I'm asked to find the exact value of cosine of pi over 12, now I can put this in a calculator, but the calculator is going to give me a decimal answer, which is not going to be terminating. So it's not going to be an exact value. So if I'm being specifically asked for an exact value, I need to do something other than put it in a calculator. And so I'm going to look at this angle that I'm being asked about, which is pi over 12. And I'm going to see if I can come up with a way of getting pi over 12 using angles from the unit circle. So for example, if I try using pi over 4, nope, let's go the other way. Make this pi over 3 minus pi over 4. That's the same as 4 pi over 12 minus 3 pi over 12, which does indeed equal pi over 12. Okay, so I can rewrite this cosine of pi over 12 as the cosine of pi over 3 minus pi over 4. And then I can go to my sum and difference identities, and I can use that to rewrite this. So for the cosine of a difference, I have the cosine of the first angle times the cosine of the second angle. And then I'm adding the sine of the first angle times the sine of the second angle. And because these are now the special angles from the unit circle, we should know the values of each of these. So a cosine of pi over 3 is going to be 1/2. The cosine of pi over 4 will be root 2 over 2. The sine of pi over 3 will be root 3 over 2. And the sine of pi over 4 will be root 2 over 2. Now, if we combine each of these terms, this is going to be a root 2 over 4. And this will be a root 6 over 4. And because I have a common denominator, I can combine my numerators and make my answer root 2 plus root 6 all over 4. Now, it may not be the prettiest answer, but it is an exact answer. And if you were to put this into a calculator and then put this into a calculator, you would find that the decimals would be equivalent. Okay. Now, sometimes it's not a specific angle measure that you're being asked to find the trig ratio for, but you're going to get some information that's going to help you to still find the trig ratio, even if you don't know the angle itself. And again, you're going to need to use identities to find this. So here's an example where it's asking you to find the exact value of the sine of 2u, given that the cosine of u is equal to 5/13, and you know that the angle u is between 3 pi over 2 and 2 pi. Now, in these cases, I like to start with a little sketch. So I know that I'm in the fourth quadrant. So I've got some terminal side that comes down this way. And if I made a right triangle out of that, this would be my angle. So this would be the reference angle for u. And cosine being adjacent over hypotenuse means that I know that this side, the adjacent side, would be the +5, because I went to the right here, so that's positive. And my hypotenuse is going to be a 13. Okay. I don't know this side at the moment. So I can use Pythagorean theorem. Call that B. (169 minus 25 ends up being 144. So if I take the square root of 144, I'm going to get 12. But because I'm going down into the fourth quadrant, it's going to be a -12. Okay. So now, if I'm looking for the sine of 2u, I use the identity, which says that sine of 2u is equal to 2 times the sine of u times the cosine of u. And I know what cosine is already because it was given. And from what was given, I can find what the sine of u was. So sine of u is now the opposite, which is -12 over the hypotenuse of 13. So even though I don't know how big 2u is, what measure that is, or even what u is, I do know the ratios associated with u, and the identity will help me to find the ratio associated with 2u. So I substitute in, the sine of u is the -12 over 13. The cosine of u is the 5 over 13 I was given, and then we multiply. So this is going to be -120 for my numerator and 169 for my denominator. Okay. So I hope that you found this helpful. If you would like to see other concepts that you need to refresh or review, please check out my Gordon Global Math page on YouTube. Videos covering Algebra 2 and pre-calculus concepts will be added throughout the spring of 2025. Thanks for watching.